This is the second video on viscosity, critical velocity, and Reynolds number. Now, what is critical velocity? The definition goes as the maximum velocity of a fluid up to which the flow of the liquid is streamlined and beyond which the flow becomes turbulent. It is regarded as the critical velocity for that fluid. We had already discussed about streamlined motion and turbulent motion in the previous video. On gradually increasing the velocity of a fluid, the streamlined flow does not become turbulent abruptly. That means there is a particular margin or margin of critical velocity above which the motion turns into turbulence, but it does not happen abruptly. We have to follow a special number called the Reynolds number to determine whether the fluid motion is streamline or semi-streamline, that means streamline mixed with turbulent or pure turbulent. So for that we need to first understand what are the factors on which this critical velocity of a fluid depends on. So if you can write now, the dependency factors have been found out from experimental verifications and not from any other else thing. So experimental verifications, critical velocity, you can write Vc. What is critical velocity? We can write it as Vc. This as Vc. So critical velocity is inversely proportional to the density of the fluid. Inversely proportional to the density of the fluid. So rho is the, suppose we take it to be the density of fluid. Again, Vc or velocity critical is directly proportional to the coefficient of viscosity, that is eta. Eta was what was coefficient of viscosity. And one more thing, that is it depends or it's inversely proportional to the characteristic length. Inversely proportional to the characteristic length. L is known as the characteristic length. Now, what is characteristic length? In simple language, we can say characteristic length is the diameter of the tube through which the fluid is flowing. Diameter of tube through which the fluid is flowing. Now, combining all these factors by the process of joint variation, we get eta by rho L, and if we place an equal to sign, we need a proportionality constant. That proportionality constant is written as, in some books you will get as R, in some books it will be N. Eta by rho L. The proportionality constant Ne here is known as the Reynolds number. This proportionality constant, or rather N, you can write Ne or N. Here this is known as the Reynolds number. Now, if for a liquid rho eta unknown and its critical velocity Vc can be determined experimentally during its flow through a tube of diameter L. From this equation, we find that there is a margin called 2300, that the value of Reynolds number 2300, so that the streamlined motion gets converted to turbulent motion. But this is actually not the fact. In some books you will find that the margin is written as 2300 Reynolds number. Reynolds is a pure number. This has got no dimension. We can write here dimensionless, or dimension is 1. So you can prove it like that, because if we take Reynolds number N equal to Vc rho L by eta, and place the dimensions of and replace the dimensions, we get ml minus 3, L into Lt minus 1, Vc is Lt minus 1, rho is ml minus 3, L is L, and eta we have already found out ml minus 1, T minus 1. So it becomes equal to 1. So I have said that it is a dimensionless quantity. Now, to understand, we take that streamline to turbulent. What happens? I draw two lines. That means Within this range, the motion is absolutely pure, streamline, and beyond this line, it is clearly a pure turbulent motion. But in this range, it is a mixed motion. Streamline and turbulency occurs at the same time. I had already said that this change does not occur abruptly. So streamline gets converted to turbulent. Now, if I take the value here to be 2000, here to be 3000, and I draw a line like this, which has got the value of 2300. That means in this portion, streamline and turbulency are mixed with each other, with a part of streamline more than that of the turbulent, whereas in this part it is also a mixed streamline and turbulent motion, but the turbulence is more. And after crossing 3000, the value of Reynolds number, after it has crossed 3000, the motion will be completely turbulent. Terminal velocity of a body in a viscous medium leading to Stokes law. Now, when a body falls through a viscous medium, now suppose this is a viscous medium, so suppose there is oil and an aluminium ball is falling through it, downward motion. Now, when a body falls through a viscous medium, it drags a layer of the fluid. Uh, adjacent to it because of adhesion. So it drags a layer of fluid due to adhesive force or adhesion. But the fluid layers at a large distance, from the body are at rest. They are at rest. As a result, there is relative motion between different layers of the fluid. There is relative motion between the different layers of the fluid at different distances from the body. Layers adjacent to it and layers far away from it. But the viscosity, what is viscosity? What is its property? It always opposes this relative motion. Now, this opposing force due to viscosity increases with increase in the velocity of the body. As the velocity of the body increases, the force or the opposing force due to viscosity, it also increases in the upward direction. If the body is very small in size, then after an interval of time, the opposing upward force becomes equal to the downward force that causes acceleration of the body. Now, what force causes acceleration of the body? That is, the downward force means the weight of the body. The weight of the body is acting downwards, causing a downward acceleration, whereas the viscous force is opposing this motion, opposing upward force. But if the body is small, what happens? This opposing force becomes equal to the downward force. The effective force acting on the body becomes zero. The effective force becomes zero. That means one force acting downwards, another force acting upwards. The weight of the body acting downwards and the viscous drag acting in the opposite direction. These two neutralizes each other, so the effective force is equal to zero. Now, as the body was already in motion, the body will continue to be in motion but with a uniform velocity. As the effective force is zero, we can say that acceleration becomes equal to zero. But as the body was already in motion, the body will not stop. It will move with uniform velocity. So when we had released the body from the top, there was acceleration. But after a fall of a particular distance, we find that this effective force becomes equal to zero, and the body then falls with a velocity that is uniform, known as the terminal velocity. Stokes' law. He proved that if a small sphere of radius r is falling with a terminal velocity v through a medium of viscosity eta, then the opposing force acting on the body due to viscosity is given by F is equal to 6 pi eta rv. Eta means coefficient of viscosity, r I've already mentioned small sphere of radius r, and v is the terminal velocity. Now when he proved this formula, he assumed some points. The first point was the fluid medium must be infinite and homogeneous. These points you will get in the book. The fluid medium must be infinite and homogeneous. Point number 2, the sphere must be rigid with a smooth surface. Number 3, the sphere must not slip when falling through the medium. The sphere must not slip. That means there must be frictional force. The fourth point, the fluid motion adjacent to the falling sphere must be streamlined. Fifth point, the sphere must be small in size, but it must be greater than the intermolecular distance of the medium. Now, how to find the equation of terminal velocity? Equation of terminal velocity. Equation of terminal velocity we can do if the density of the material, if we take the density of the material of the sphere is rho, so rho you can take it as the density of material of sphere. So 4/3 pi r cube is the volume, multiplied by the density gives the mass, and multiplied by g gives the weight. Now what is this weight of the sphere? Weight of sphere. Now when the sphere is falling through a medium of suppose fluid, sphere falling through fluid medium of sigma density, then upward buoyant force equal to 4/3 pi r cube, because the whole sphere has displaced some portion of the fluid, whole volume of fluid, 4/3 pi r cube into sigma into g. So the resultant force, downward force was 4/3 pi r cube rho g minus 4/3 pi r cube sigma g. Now this force must be equal to rho minus sigma into g, must be equal to the Stokes law, formula for the Stokes law, 6 pi eta rv. So we can write 6 pi eta rv is equal to 4/3 pi r cube rho minus sigma into g. V is equal to 2/9 r square rho minus sigma into g by eta. So this is the formula for the terminal velocity of a sphere falling through a fluid. Now terminal velocity is directly proportional to the square of the radius of the wire. Terminal velocity you can say is directly proportional to the difference of densities of the material of the sphere and that of the medium, and inversely proportional to the coefficient of viscosity of the medium. Rate of flow of liquid. This is a pipe. Area of cross section of the tube is alpha. Area of cross section of the tube is alpha. The velocity of flow of the fluid is v. Now what does the rate of flow of mean? Rate of flow of a liquid means through a tube means the volume of liquid flowing through any cross section of the tube per second. So volume of liquid through cross section, any cross section, by what do we write, per second time. So this is known as the rate of flow. Now this is the case for streamline and an incompressible liquid. Streamline flow of a perfectly incompressible liquid. Now, how to find out volume of the liquid through the volume of liquid through any cross section means cross section is alpha. So you can write uh, rate of flow. Volume of liquid through cross section by time means rate of flow of the liquid is equal to V into alpha. Now see, V is velocity meter by second into alpha is meter square. So it becomes meter cube per second. That means volume per second. Volume of liquid per unit time. So V into alpha gives the rate of flow. Now the mass of liquid flow per second that is velocity of flow into cross sectional area into multiply this with density rho. So you can write V alpha rho, where rho is the density of liquid. You can straightforward write the liquid or the fluid that is flowing through it. Density of the liquid, so it will be V alpha rho. Now equation of continuity. We take a cross section but of different shape. This is a cross section, a large cross section. This is a small cross section. The velocity, let it be alpha 1, this be alpha 2. Velocity here is v1, velocity here is v2. Now what happens? The mass of the fluid flowing through this cross section and the mass of the liquid or the fluid passing through this cross section remains the same. So mass through alpha 1 is equal to mass through alpha 2. Now what is mass? V1 alpha 1 rho and V2 alpha 2 rho. So rho and rho get cancelled. V1 alpha 1 is equal to V2 alpha 2. This is known as the equation of continuity, or we can write V into alpha is constant or V inversely proportional to 1 by alpha. So velocity at a larger cross section is small, whereas the velocity in a smaller cross section has a larger velocity. Smaller cross section has larger velocity. Energy of liquid in steady flow. There are three forms of energy. One is kinetic energy, second one is potential energy, and third one is pressure energy or energy due to pressure. Now the first one is kinetic energy. We know all to be half mv square. Now kinetic energy per unit volume becomes half m by v square. V is the volume, so m by v means density, half rho v square. Second is the potential energy. The potential energy is equal to mgh. The potential energy per unit volume means m by v gh. M by v is equal to rho gh. And third one is the pressure energy, which eventually comes out to be P. Now how did we get P? Energy means, in other words, it is work by volume. Every time we have found out energy by volume, that means energy work is equal to force into displacement. Now suppose displacement is x, volume is alpha into x into rho. F is equal to the force is pressure into area of cross section, pressure into area into x by alpha x rho. X gets cancelled, so it becomes volume is alpha x, not rho. So alpha x gets cancelled, becomes equal to P. So work by volume or work done per unit volume is P. Bernoulli's theorem. For a streamlined flow of an ideal fluid, the sum of the potential energy, kinetic energy and energy due to pressure per unit volume we have already found out. This was the kinetic energy per unit volume. This is the potential energy per unit volume. This is the pressure energy per unit volume. It remains constant. That is for a streamline flow. Everything we are trying to explain is the case of streamline. So energy per unit volume, sum of these energies always remains constant. Now if we divide the full equation by the density, we get half v square plus gh plus p by rho. Constant by density, density is also equal to constant, so this becomes another constant. Now if we divide this by g again, we get v square by 2g plus h plus p by rho g. G is also a constant, so constant by g means that is also g. Now v square by 2g is known as the velocity head. Velocity head, they are known as head. This is known as the elevation head, the height, and this is known as the pressure head. Now one or two applications of the Bernoulli's theorem, velocity of efflux of a liquid, and Torricelli's theorem. We had already discussed about the velocity of efflux in the previous chapter of hydrostatics, but in this case we have to find out the velocity. The formula came out like this: v is equal to square root of 2gh. Now we have to derive the formula using the Bernoulli's theorem. So the height of this nozzle from the ground level is h1. The height of the free surface of water is h2. So h2 minus h1, we can write h2 minus h1 is equal to h. This is the height h. Now using Bernoulli's theorem, we can write 0 plus h2 plus p by rho g is equal to v square by 2g plus h1 plus p by rho g. Now to give the explanation of this form, we had already said using Bernoulli's theorem, that means sum of the energies is equal to sum of the energies at point h1. h2 and h1 remains the same. Now what happens? We take this velocity at 0. That means the velocity of this layer, we take it to be 0. But in actual case, the layer slowly comes downwards as the liquid tries to flow out. As the liquid flows out, this level should move down, but the motion is so slow that we can take it to be almost 0. Plus h2 plus rho p by rho g. The value of the pressure here is p. Now for this height, at this case, we can take v square by 2g. That means the velocity of flow of the liquid is v. So v square by 2g plus h1 plus p by rho g. Because this two remains the same, we can write that v square by 2g is equal to h, or v square is equal to 2gh, or v is equal to square root of 2gh. This is the velocity of efflux in a liquid through a small hole, and this is known as the Torricelli's formula. This is also known as the Torricelli's formula. Now second application, we can take the venturimeter. What is a venturimeter? You can draw it like this. Now if we take this cross section and this cross section, we see this cross section is very small. So if this area of cross section is alpha 1, the velocity of the liquid is v1. Alpha 2, and the velocity here is v2. We find the liquid level rises more in this, where the liquid level here rises less by less amount. Now why does this happen? A fluid is flowing through this mouth, through the tube. Now if the amount of flow, you take it to be 10, this is a larger area, the velocity will be less, so less pressure. So the pressure is used up more the maximum part of the pressure is used to make the liquid rise in this tube, whereas here the pressure is more, so the liquid level rising in the tube is less than this one. Here the pressure is less, so it rises more. The pressure is used up more to rise this level, whereas in this case it rises very less amount. So we can write v1 square by 2g. Now height portion will be 0, h is 0 because this is the same horizontal level. As both the tubes are in the same horizontal level, we take the height to be equal to 0. P1 by rho g is equal to v square by 2g plus P2 by rho g. Now we can take the velocities onto one side and the densities onto the other side. So we can write P1 minus P2 onto this side by rho g is equal to V2 square minus V1 square by 2g. So g and g gets cancelled. P1 minus P2 is equal to rho comes onto this side, rho by 2 V2 square minus V1 square. So P1 minus P2, this was height h1, this was height h2. The difference in the height is h. So you can write h rho g is equal to rho by 2 V2 square minus V1 square. So here rho gets eliminated and we can write here the value of h as P1 minus P2 h rho g, rho by 2 V2 minus square minus V1 square, and from this rho gets cancelled out. We can write h is equal to 1 by 2g V2 square minus V1 square. V2 square minus V1 square. So h comes out to be 1 by 2g V2 square minus V1 square. If we take V2 square common from it, we get 1 minus V1 by V2, like this. Now using the equation of continuity, alpha 1 V1 is equal to alpha 2 V2. From this we can write V1 by V2 is equal to alpha 2 by alpha 1. So we can replace V1 by V2 with alpha 2 by alpha 1. So the equation can be written as V2 square by 2g 1 minus alpha 2 by alpha 1 whole square. So V2 square is equal to 2gh alpha 1 square by alpha 1 square minus alpha 2 square, finding out the velocity at point number 2. So V2 square is equal to 2gh alpha 1 square by alpha 1 square minus alpha 2 square, from where we can get V2 is equal to square root of 2gh alpha 1 by root over alpha 1 square minus alpha 2 square. So this is one formula, and volume of liquid flowing per second, that is V, is alpha 2 V2. The volume is V, flowing per second, alpha 2 into V2. We replace V2, the form of V2, into this equation. So what happens? It becomes alpha 1 alpha 2, here is alpha 1 alpha 2, square root of 2gh by root over alpha 1 square minus alpha 2 square. We can write it in this form also, total under the root square root of 2gh by alpha 1 square minus alpha 2 square.